off we go. Right, there we are. We are now on. So that's me, that's Emacs, which is where we're going to be spending our time. Right. Okay, so what I'm going to talk to you today about is one of the possible versions of what the future of programming is going to be. If you imagine what the world looked like before Java, everybody was going on about how functional languages would never take off, garbage collection is ludicrous, you'll never get good runtime, blah, blah, blah. Then Java happens, and everybody's like, oh, garbage collection, of course, you'd want anything else. Right, so if you imagine what the timescale on that is, so Lisp is kind of, well, okay, actually, lambda calculus is about the 1930s, Lisp is the late 1950s, standard ML, which has got pretty much most of the features that Java then brought in, that's late 1970s, and Java is mid-1990s. So depending on where you want to start, you get at least a 20-year lag from languages being out in research labs to making it out into commercial practice. And this is definitely a research lab language. So I expect that nobody will ever be hired to develop expensive middleware systems in Agda. But Agda may well, the features that are in Agda may well be in whatever the next Java is. So whatever language comes along that makes everybody dance up and down, in the same way that Java did in the mid-90s and JavaScript did about 5 years ago. So there's going to be a new language will come along at some point, and this is one of the possibilities for what it's going to look like. Right, so what is Agda? Right, well, Agda's got two hats, and the interesting thing is it can do both of them at the same time. So it's a foundation of mathematics, and it's a programming language. And this means there's a kind of slightly weird skill set that you need in order to be hacking around, certainly with the language specification itself. But even when you're programming with it, you have to have you have to be wearing both of these hats quite often. So one of them is that there's a formalization of constructive logic. It's done in dependent type theory. The semantics are given categorically. Blah 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 blah. Right. I am not going to talk about any of that today, and instead I'm going to talk about the kind of pragmatic, hacky side of Agda. But I'm still going to show you kind of some of the features that Agda brings to the table. So pragmatically, the thing that dependent types are doing for you is that they're allowing user-customized static analysis. So if you think about what it's like writing in a statically typed programming language like Java, you can write whatever code you want. So at runtime, you can get whatever behavior you want out of the machine. But at compile time, you're stuck with the type system that Oracle gives you. And if you want a different type system, tough. Go away, you're out of luck. Whereas in dependently typed languages, you can put arbitrary user code into the type system. So the type system and the programming language are the same language. There's not this funny thing in Java where, if you want to apply a function, it's, f open paren stuff close paren. If you want to apply a type argument, it's angle brackets. They're different programming languages in Java. Whereas in languages like Agda, it's the same programming language for you writing your type system as for writing your regular code. And this means you can do interesting custom static analysis. I'll show you a little example of that. The IDE has got different features than IDEs like Eclipse. I mean, you're going to see we're going to be running it in Emacs here. So there's rough edges because it's an Emacs IDE, but there's some features that, my word, I wish Eclipse had. So I'll also talk about that when we come to it. And in particular, it's got a very interactive feeling. So programming in something like Eclipse, you get the feeling you are shoving code at Eclipse, and occasionally you can get it to shove code at you using something like a wizard, but it's not very interactive. Whereas in the IDE for Agda, as you'll see in a moment, is very interactive. So it's kind of feeling of like the world's geekiest video game. And it's got the usual kind of compiler stuff like backends to Haskell and C and JavaScript. So I did the JavaScript backend. Oh, I should say, Agda is not just me. So Agda it's it originally came out of Chalmers University, starting about 10 years ago, and it's got developers in Chalmers and Nottingham and University of Munich. So there's a decent-sized development. It's still a small research language, but there's a decent-sized development team. It's not just me. But I did do the JavaScript backend and the associated libraries for web programming. So what we're trying to do here, one of the ways of viewing this is we're trying to get a sweet spot between currently, if you're going to go out and pick a language, you have to pretty much pick one that's either dynamically typed or statically typed. There's a few other weird options, like what I'm going to talk about here, but pretty much that's what the landscape looks like. And this means that, well, okay, so in both cases you write your code, but then how do you try to convince yourself that your code is correct? Well, if you're in a dynamic language like JavaScript, welcome to unit testing. And you write tests, and then you write more tests, and then even more tests, and that is your life. And if you're lucky, you get a tool which tells you about whether you've got good test coverage or not. But that is the only mechanism you have for determining correctness. If you're in statically typed languages like Java, you actually get a much stronger static analysis that the language gives you, which is giving you quite strong memory and memory safety guarantees. But there's a penalty to that, which is you're stuck with the Java type system. And sometimes that really gets in the way, and you end up having to switch it off using casting. So if you look at a lot of production Java code, you'll quite regularly see casts scattered through it, because there's places where the programmer had an invariant in their mind that they could not convince the Java type system was true. Right, and so the idea is we're trying to find something that's sitting between these, where you get the benefits of static analysis, but still have the flexibility of being able to do whatever code you like. And that's because we've got user customizable static analysis. Right, and another way of looking at this is there's a sliding scale of unit testing, where you start at one end, and you're just doing regular old unit tests. You've got hardwired data in, you run your test, it either succeeds or fails. Right, your next level up is you go, well, that's getting a bit tiresome. Rather than me writing all the data, I'll get a randomizer to generate the data for me and stress test my code. And that's okay until you discover, well, it's spending most of its time. There's a search space here of data values I can feed in, and most of it is just doing a flat search through that space. And really, I'd like it to focus on the corner cases. So you'd like directed randomized testing. And that gets you into wanting things like symbolic execution and theorem proving. And then the last thing is you'd like to have unit tests with exhaustive coverage. All right, and that's exhaustive over infinite data domains, like the natural numbers. And so you might think, how on earth are we going to do that? You can't do exhaustive testing on infinite data. All right, well, I'll switch me off because we're about to go into demo mode. Right, okay. So another name for exhaustive unit testing over infinite data domains is mathematical theorems. And that's where the idea that what you're doing is you're programming with something that's simultaneously a theorem prover and a programming language comes in. Right, okay, so that's my quick introduction. At this point, I'm going to go out of me talking and you listening mode, and I'm going to be a bit more interactive with the system, and hopefully you guys are going to be a bit more interactive as well. First of all, this is a quick show of hands. Who here has programmed with a functional programming language of the kind of Haskell, standard ML, F#, that kind of variety? All right, so that's about, what, 4 or 5 people. Okay, right, so for the 4 or 5 people here, you can go to sleep during the next, 20 minutes or so. For everybody else, you're about to see, this is going to be your first exposure to a Haskell-like language. So Agda builds on the Haskell worldview. So the last part of it is going to be a bit of a shock to the system. so you're going to have, seeing functional programming for the first time is a bit of a shock. Going straight from functional programming into dependent types, woo boy, right? So I suspect there are a lot of people that this middle section I'm about to do about Haskell-like programming is going to be the main benefit. Right, so I'm about to give a demo of the kind of core Haskell-like language, and then I'll give a demo of the custom static analysis. Right, okay, and if you want documentation, there's a wiki. If you want to install this on a Debian-based system, it's apt-get install Agda. Agda bin gets you the command line tools, and Agda mode gets you the Emacs mode we're about to use. And this file is a gist up on GitHub. Right, okay, so here we are. We are doing a demo. Right, okay, so normally, if you're writing in Agda, you don't actually have to do everything on the raw metal. There's actually standard libraries for things like the booleans that you would normally use. But I'm going to do it all from the bare metal, so you can get a flight feeling for the language, rather than like there's this mysterious library. What's going on here? So this is a type for booleans. So what we're declaring is here's a new data type, and it's got two constructors. You can build it either using as true or as false. Ta-da! Right, there we go. Right, and we're in the Emacs Agda mode. So one of the things I can do now is I can type Control-C, Control-L, and now it's loaded the file in. You can see it's done syntax highlighting. For everything I'm going to do here, you could, if you wanted to, I suppose, use this funny thing called a pull-down menu. But this is Emacs, so of course I'm going to be typing Control-C, Control-blah, which is what Emacs is all about. Right. And there's a few other things you can do. So you can say Control-C, Control-N, for instance, and you can give it an expression. And so you can say true. All right, okay. And it says, yay, I evaluated true. And it was true. That's not very surprising. All right, and you can also say Control-C, Control-D. I can say what's the type. So I can say what's the type of true. And, oh, okay, so true is Boolean. Okay, so you can kind of interact with the evaluation system. So if you're used to kind of debugging systems for languages like JavaScript, where you can evaluate them dynamically, that's pretty much what's going on here. Right, okay. This is the interesting bit, and this is the feature. Oh my goodness, if anybody out there goes on and has a career designing IDEs, this is the feature that I wish every IDE had, because there's nothing specific to Agda about it, which is when you're writing a program, you don't actually sit down and carve an entire program and it's beautiful and finished and perfect. And instead, what you do is you write a program as you go along, and it's got bits missing from it. And most IDEs do not understand that. They don't have an idea that you're working on a program with holes in it, whereas Agda does. So here, down here, we're going to define ourselves a negation function on Booleans. So it's going to be not X. So it's going to take in a Boolean and give you a Boolean back. It's not the world's most exciting function. But no, it's missing its definition right now. And that's the new feature that Agda's IDE has, is it explicitly has an idea of here's a program, it's got a hole in it. Right, okay. Right. So now, what are we going to do? We're going to define negation. So what do you think we should, how do you think we could define negation on the Booleans? Well, what's X? What's the type of X? It's a bool. All right, so what's its possible values? Okay, right. So how many cases do you think we've got? 2, right, okay. So if you're in your average programming language now, you'd actually have to go and edit the file here. Whereas this is the other feature, another feature that Agda's got, is it actually explicitly understands the idea that you can do case statements or pattern matching. Right, so I've told it on variable X, Control-C, Control-C, I would like you to do a case split. And now it's about to do a case analysis. And it's worked out that there's actually only 2 values that X could have, true or false. Good luck doing that in JavaScript. Right, okay, and now we've got and what it's done is it's taken previously we had 1 hole, and now it's split it into 2 holes, and they're both down here. You can see they're both of type Boolean. Right, okay, well, let's go to the first one. Right, what's not true? False, right, okay. And Control-C, Control-R is the magic that says, you know, I've just given you the value for the hole. Please fill it in. Okay, and not false is true. Yay, thank you. It's not a trick question. You're thinking, oh, there must be something clever here. Right, okay, so let's do another one of those. Okay, so what do you think we're going to do here? We're doing conjunction. So we're doing X and Y. Okay, so what do you think I'm about to do here? So what are my cases going to be? Okay, so what? So check. So what is it I'm going to case split on? Okay, right. I'll case split on x. Right, there we go. Right, so true and y is y. Yeah, there we go. And false and y is false. Yeah, right. Ah! Did you know that typing standing up is sometimes hard? All right, there we go. Yay, cool. All right. Right, so that's the Booleans. Let's do the natural numbers. Right, so right, okay. So again, in most languages, the natural numbers would be built in. So you just be given, here's your magic integer type. Deal with it. In Agda, they're not. They're actually a data type that you can define yourself. There's one piece of magic the compiler gives you, which is that it's incredibly tedious writing numbers in unary. So if you look at the definition of the natural numbers up there, there's two cases. I mean, a number is either 0 or it's the successor of some number. And those are your only two cases. But writing suck 0, that gets a bit tiresome. So really what you want to be able to write is you want to be able to write numbers like 3 as shorthand. All right, okay. So let's just make sure that that's true. So I'll just normalize. So I'm going to say, what is the successor of 0? Hooray! Right, that's 2. Good. Right, hooray. Okay, and that's that piece of magic. So that I will give you, there is a piece of compiler magic there, which is that built-in to tell it that we're using that syntax. Right, okay, so let's write some functions over that. Right, so addition. What am I going to case split on? Yep. Yep. Right, okay, so there's two cases. Either x is 0 or it's not. Okay, and so you can see I did a case split there, and it will do the two cases. One of them is 0, and the other one is successor of some variable. Now, slightly annoyingly, Agda sometimes does a really bad job of picking variable names, because it's not actually a magic artificial intelligence system which knows about good variable names. So I'm going to actually rename the variables to something a bit more sensible there. Right, okay, right, so now we've got two cases. So what's 0 plus y? Right. And, right now, successor of x plus y is, yes, yeah, so it's the successor, and again, I can't type standing up, of x plus y. I still can't type. What's going on here? Has it gone into insert mode? Oh, that's right. It was in insert mode. That's what was going on. Yeah, there we go. Right. Okay. And similarly, for doing equality, we can do a case split on x. Okay. So now, 0 equals y. So yeah, so the problem is that again, so here we can't actually say what the answer is, because I mean, y could be any old number, so it might be 0, it might not. So yeah. So what we do is we do another case analysis. So in fact, before we do that, I'll rename these variables because those are badly named variables. Right. Okay. So the idea is, again we can case split on y. Okay, and now 0 equals 0 is true. And 0 equals the successor of y is false. Yeah, 0 is not the successor of anything. Typing standing up is difficult. Right, okay, and then we do the same thing down here. We do a case split on y. Okay, and now successor of x equals 0 is false. And the successor of x equals the successor of y. Yeah, that's just true when x equals. There we go. Right. Okay, load it all in. Yay. Okay, let's just do some checks to make sure we're right. All right, let's see. 2 plus 2. 2 plus 2 is 4. Hooray. 2 plus 2 equals, 4. 2 plus 2 equals 4 is true. Hooray. Right, okay. This is all looking fairly good. And you know, if you were in your average programming language, those kind of unit tests, that pretty much be all you could do. Right, okay. I pre-did less than, because I think we're getting a bit tired of that. Right, and I'll do so at this point, this is kind of like the classic example in Haskell. So still we're inside Haskell at the moment. And the kind of classic example in Haskell is polymorphic lists. So I can do things like, let's see, I can take 1 and I can put it on the front of 2, and I can put that on the front of the empty list. So cons 1, cons 2, nil. All right, okay, that's that. And I can do the same thing with true. In fact, I can't type. Put on the front of false. Put on the front of the empty list. All right. But if I try doing something like 1 stuck on the front of true, stuck on the front of the empty list. Right. Okay. Type checker fails because it's saying, tough, you tried building a heterogeneous list. And this is the type of homogeneous lists. Everything in the list has to be of the same type. So I'm not going to allow you to build that. So this is a data type for lists where everything in it is the same thing. So if you're used to the container types, the polymorphic container types in Java, that's this. This is a simple example of that. Okay, so the data type here, it isn't just lists. It's lists where we keep track of what the type of the elements is. So for example, if I get it to describe 1 cons nil, right, well that's a list of numbers. Whereas true cons nil, right, try again. True cons nil, right, that's a list of booleans. So we're keeping track in the type system of what the types of the elements are. And so, you know, this is, apart from the syntax, this is pretty much what you write in Haskell. So, you know, we've got a list, it's parameterized on a type, and it is a type, and it's either empty or it's a cons cell. Oh, yeah, okay. Right. That there is underscore 170. Well, that's a really bad notation for it's a meta variable. I couldn't work out what its type is. So it's so in this case it can't actually. It doesn't know. Whereas when you stick a 1 on the front, Hindley-Milner type analysis, it can infer the type at that point. Right. Okay. So. Here is your traditional function first function on lists, which is going to concatenate 2 lists together. So we're going to stick x's onto the front of y's. Right, okay, so case analysis. Right, so there's 2 cases here. And yet again, it chose really bad variable names for the variables, so I'm going to rename them. Right. So empty list. Right, yep. If you stick the empty list on the front of y's, then you get y's back. Right, and if you stick x on the front of x's stuck on the front of y's, yeah, then it's x stuck on the front of something or other, and then that something or other is x's plus y's. Right. And the compiler is a bit too clever for its own good and worked out that that's unambiguous, but it's easier to read the code if you put the parentheses in explicitly. Right. Cool. So now we can actually stick lists together. So I can say, you know, 1 stuck on the front of empty, concatenated with 2 stuck on the front of empty. And yay, we get the list 1, 2. Out. Woo! Yay! Yay! Right. Okay, so that's your kind of really swift introduction to Haskell-like programming languages. Now's when it gets weird. Right, okay. So,
For each symbol in the definition of the function, and not in, I mean, not for the data, for the list of the data type.
sorry?
I mean, I see that you have a for each symbol there.
Oh, okay. Yeah, I should say. Yeah, I kind of ignored that. So that is saying that this function here is polymorphic in A. So it's saying for any type A you give it, you give me a list of A's and a list of A's, and I'll give you a list of A's back.
But you don't use that for polymorphic types.
Oh, what, up there? You mean in the actual definition?
You don't have that for each there.
You could actually use that syntax up here. So you could, I mean, the for all syntax and the parameterization syntax are actually syntax sugars for each other. So I could, if I wanted to, put the parameter in using a for all in certain cases. So there is some syntactic going on, but on the whole, most of the time they're the same thing. Right, okay. So what I'm going to do now is, so that was your kind of beginner Haskell code. Everybody's first Haskell program practically is concatenating lists together. Right, now what I'm going to give you is everybody's first dependently typed program, which is I'm going to do some custom static analysis. And the custom static analysis I'm going to do is tracking the length of a list. And the reason for doing this is index bound checking. So if you imagine you're in your average programming language, you've been given let's say an array, and now you'd like to get an element out of that array. Right, well you get some choices here. You can either be in a language like C, where it just works, and if you offset out of the array bounds, well, you get something back, and you can do buffer overflow attacks this way. And this is where the land of buffer overflow attacks. Right, so that's one option you get. A little bit of a problem for security. The other option you get is you get languages like Java or JavaScript, where they actually track at runtime, they track the length of the array, and when you do an index into an array, it does a bounds check to make sure that the value is correct. And that means that, congratulations, you don't get any more buffer overflow attacks, but it comes at a cost, which is you're having to do that check every time you do an array access. And that destroys pipelining in your architecture, and it's a bit of a nightmare. So it would be nice if we could actually do array bounds checking and actually make it that the indexing function is total. It'll always give you a result back. And the reason why is you just can't. It's statically checking to make sure that you're indexing into the array properly. And that's why we need to track the length of the list, because we need to make sure that the array element's actually there. Right, so now, this is the same type. If you look, there's not much difference between these types, except that there's an extra parameter. Now, suddenly, lists aren't just a set, it's not a type anymore, it's a function from numbers into types. And that means we can now pass in another parameter, which is the length of the list. Right, okay, so the length of the empty list is 0. All right. Okay. Now, what about a cons cell? What's the length of a list if it's had something stuck on the front of it? So this is the head. That's the tail. Yeah. So it's 1 plus length of the tail. All right. That's what this universal quantifier is going to give me. So I'm going to say, well, let's universally quantify over any tail of length n, and now the whole thing is going to have length 1 plus n. I'll reload that in. Oh, and that piece of yellow ink disappeared. That's nice, because now it knows, that n is a number. Oh, right. Right, okay. So now let's look at our old append function. Right, so this is the same append function as before, except now what it's doing is you give it a list of length m, and a list of length n, and the length of the whole thing is m plus n. And the thing that's pretty cool is, actually, you can just cut and paste the code. So I'm just going to take that. I mean, we could do the case analysis down here, so if you wanted to, you can go through and do it. But I failed to do the cut and paste there. Right, okay, let's cut and paste the code in. The only thing I need to do is I need to rename some of the symbols. So So some of these things have changed name. La la la. There we go. I think I've got all of them. Load it in. There you go. Right. So now exactly the same code, modulo changing the names, and we've managed to persuade Agda that when you concatenate two lists together, you take a length m list and a length n list, and you get a length m plus n list out. All right, that's kind of cool. Right, next thing we can do with this idea. So now we've got this idea that you can parameterize types, not just on other types, loads of languages, like even Java lets you do that. But you can also now parameterize them on data. You can have user-defined, the regular old expression language is now allowed to sit inside your type language. And here's another example of that. So up there, in the type of length tracking lists, we were keeping track of a number. Right, now we're going to keep track of something simpler. We're going to keep track of a Boolean. So this type here is going to be a type for unit tests. So it's only got one constructor. That's OK. That's the only thing you can do to build this thing. And what it does is it allows you to build something where the Boolean you gave it is true. What on earth use is that? All right, OK. And the reason why that's useful is that you can write unit tests using it. So here we've got a unit test, and this unit test is checking that 1 isn't less than 1. All right, well, there you go. All right, and I'll just load that in, so you can see it really does go through the type checker. There we go, it's been pre-printed now, so the type checker liked it. Right, so that's it saying, yeah, it really is true that I ran this unit test, and 1 isn't less than 1, big deal. But so note, we're running unit tests during compilation. We've not got a separate test harness where we had to run our unit tests using a JUnit or whatever your favorite unit testing framework is. We're actually running them during the same compile, edit, debug cycle. All right, okay, let's do another one. Right, well, 2 isn't less than 2. 3 isn't less than 3. All right. Well, let's just make sure that we're not doing anything stupid here. All right. So if we try saying that 1 isn't less than 3. Yep. Right. Okay. Any bets? What's going to happen now? I'm going to load this in. Yeah, it won't compile. And what's the error message it's going to give us? Right, indeed. Red ink, underlined, bad stuff. And the error message is actually, by the standards of type checking error messages, is actually fairly readable. True isn't false. The thing we gave it is a test that's false, and we've asked it to make sure it's true. So that one failed. So let's get rid of that. Right. Load that back in. Okay, so we've written a bunch of unit tests, but boy, this is getting quite tedious, right? So we checked it for 1, we've checked it for 2, we checked it for 3. At this point, if you were writing JavaScript code, you'd probably stop and go home and say, right, well, we did 3 tests. Come on, how many tests do you want? Right, okay, but now, like I said, with Agda, we can actually write exhaustive tests over infinite data domains, like the integers. So here's our exhaustive test, and it's going to say, no matter what x is, x isn't less than x. Okay, so x here, that's a number. So just like any old other function on numbers, I'm going to do a case split on it. All right, so now I've got 2 cases. Right, well, the first one is that 0 isn't less than 0. All right, well, that's just true. All right, so I can just put in OK there. All right, and for the successor, well, the successor of y, checking the successor of y is less than the successor of y, that's just checking y is less than y. So now we can do a recursive call. So I can just call myself again on y. Load it in. And there you go. Right, so now we've done an exhaustive test to make sure that x is never less than x. And another name for these exhaustive tests is mathematical theorems. And this mathematical theorem is the anti-symmetry of the total order on the natural numbers, which is not exactly a huge shock. It's like, oh my goodness, the strict order on the numbers is anti-symmetric. Wow. But you know, we've actually proved it here. And so this is an example of why there's a sliding scale of unit tests at one end and theorems at the other. All right. And so now we can actually combine these together, and I'll show you this is the problem that I said we were going to solve, which is indexing into a data structure. So this is the traditional way of doing it, and really annoyingly, you're given a list and you're given a number, and you can't get an A back because you might get an out of bounds exception. So instead, you will get a maybe A back. And in languages like Java or JavaScript, you get special null or undefined values, which do the job of this maybe for you. But still, you've got this special extra stupid case you have to deal with, and it's a cause of who knows how many errors. So Tony Hoare actually did a brilliant talk called "My $1 Billion Mistake," all about the null pointer. He's the guy who invented quicksort, did lots of brilliant stuff, but unfortunately, when he was doing this bit of the Algol 68 spec, put null pointers in, and he's done a terrific talk on this topic. So type in "My $1 Billion Mistake" Tony Hoare into Google and watch the resulting video. Right, okay, so we're doing our indexing function. Usual stuff. We're going to do a case analysis on the list. Ugh, can't type. Right. Okay, so we've got two cases now. So the first case is when it's the empty list. So what we're going to do when we get the empty list? Yeah, we can't return anything, so you just have to return nothing. So we've defined ourselves this magic nothing for exactly this case. Right, okay, now we've got a non-empty list, so we can case split on n. Right, so now if n is 0, now what?
X.
Yeah, we can return x. Oh, okay, so we can't. Sorry, silly me. I tried doing the obvious thing, and it fails, right? And it's because you have to return just x. And again, silly tagging that you have to do. Grr. All right. And now, if n's greater than 1, well, we do a recursive call.
Sorry, is x the list containing x? Or what?
Yeah, so x is the head and x is the tail.
Yeah, x is a list. Though.
Yeah, the whole thing is the list. We're pattern matched.
So I'm trying to figure out what the just.
Sorry, hang on. So what that just is? Oh, okay, because x here, that's the head of the list. So that's got type A, but we're returning a maybe A. So we have to put just on the front, because just, where's it gone? Just, there we go. Takes an A and gives you a maybe A back. Blech, blech, blech. Right, okay. But, you know, just to make sure that it's actually passing its unit tests. There we go. Not very exciting. Right. Well, it better not be a mistake. I've just managed to get it through Agda. So, unless there's a flaw with Agda's type checker. Anyway, so indexing, indexing 2 gives you, so gives you 7 because we're doing zero offset indexing, and there isn't a fifth element, so it gives you back nothing. Right. Okay. Right. So now we could do that with those length tracked lists. And now you're given a list of length m, you're given a number n, and now we can pass in an extra thing saying, look, it's okay, you will be able to do this offset. We're going to pass in a parameter saying that n is less than m. And now we can actually get an A back. We're not going to get a maybe A back. Right, so same piece of code. We'll do the case split on it, on x's. And again, it's going to do the same thing of giving me bad variable names. I'll come back to the empty list case, because that's the interesting one, in a moment. I'll do the boring case first. Right, so the boring case is we do a case analysis on n. If n is 0, we return x. The keyboard here, for some reason, I keep pressing the insert key, which is not what you want to do in Emacs. Right, okay. And look, we returned x, not some stupid tagged version of x that could remember whether it was nil or not. And when we're doing the index, when we're doing the recursive call, there we go. Right. So that's basically the same piece of code. The only thing that's different is we're passing this parameter, this n less than m parameter, around. Right. Okay. Right. Now we've got our nasty case. What are we going to do here? This is the whole reason why we had to introduce just and nothing, was to deal with exactly this case. We're trying to index into the empty list.
Well, but here m is 0 for.
Yep.
So this is an impossible case.
Indeed. Right. So what's happening is because n is 0, n is the length of the list. Right, so n is less than m. Well, that's false. There is nothing of that type. So let's have a look at the type of n is less than m. Indeed, it's false. So we've been passed in something that's impossible. You cannot be given a value of that type, and I'm going to case split on it. And let's see what happens. That's what happens. It works out. Agda, the piece of magic special syntax, Agda has special syntax for this is a pattern which cannot ever be inhabited. And note, there's no right-hand side. We did not have to give a definition there. And so Agda has managed to work out that that is an impossible case, and so you don't need to provide code for it. And just to make sure, there you go. It does in fact pass its unit test. And note, you get 7 back, not some silly just 7. There you go. And if you try doing the one that doesn't type check, there you go. Again, true isn't false. And you will never be able to come up with anything which you can put there that will actually get that through the type system. So it really has managed to stop you from doing array indexing errors. There we go. Right, so that's your, okay, I'm going to stop there slightly over time. So at this point, you've now seen kind of the waffly background idea behind Agda, its use as a Haskell-style functional programming language. So if nothing else, you've now seen something that looks a lot like Haskell, so even if that's the main thing you're taking away from me today. And the use of dependent types to do custom static analysis, so in this case, tracking array indexing. Thank you very much.
Questions?
So probably just one completely the test where you tested for all x less than y or whatever.
Oh, where's it gone? What, that one up there?
So I don't understand what it's actually doing there. It's obviously not running through all x.
Oh, yeah. There's this funny use of Agda where when you're driving it as a theorem prover, you write programs that actually you never expect people to run it because there's not much point in running it. So if you think about what that function does, I mean, it's always just going to give you OK back. So there's no point in running it. Why on earth would you ever want to run this function? Actually, in fact, I'll show you it running. I mean, so let's see. Less than asym 3. Let's make sure that 3 isn't less than 3. Oh, okay. And that's because that's the only value it could ever give back. So you've got these funny functions where you never actually run them, and all you do is they're there in order for you to get them to get the type checker to check them. because the type checker's actually got, it's got a theorem prover sitting in it. So this is so you end up using the type checker in two different ways. One of which is you use it as a regular old type checker, like you would in a language like Java or Haskell. And another way you use it is you use it as a theorem prover to make sure that statements are true exhaustively about your code. Like this anti-symmetry property.
Okay, so when you were talking about like the JavaScript and improving the test and then saying, okay, I'm happy to go home now. I mean, you're not actually running an infinite number of units.
Indeed, yes. So okay. If you want, I can give you the JavaScript version of this as well, which is contracts. It's up for grabs at the moment what the notion of correctness inside JavaScript should be. So the ECMAScript standards body is working on this, but chances are it's going to look something like contracts. And the way that contracts work is essentially they're unit tests, except that for functions you can give preconditions. So you can say, here's a precondition on you calling this function. Now, assuming you call it with that precondition, here's a postcondition. So something like, you've got you're finding an element in a sorted binary tree, and the precondition is it's a binary tree that's been sorted. The postcondition is it gives you an element that was in the binary tree. So you get precondition, postcondition pairs. So that's what contracts look like in JavaScript. And now you specify these contracts like you do here. You actually give them, saying, for all trees you give me, if you give it me with a tree that's sorted, I'll give you back a test to see whether an element was in that tree. And those can be run in a number of different ways. I mean, one of them is you just plug specific values in and test to see whether they're true. Or you can do it randomized or directed randomized search. Or indeed, people are building theorem provers for JavaScript, which will allow you to do this kind of thing. So you get a contract for your JavaScript code. Right, here's my theorem prover. I'm going to try to actually show that the theorem is true. So the stuff I'm presenting here, it's still research lab stuff to do it for Java. The theorem proving part is research lab stuff. The contracts part isn't. Contracts are very likely to come into JavaScript. They're the way that people do annotations for the expected semantics of code in JavaScript. So this stuff, this stuff isn't completely out in the stratosphere. It's likely to come to a language you might care about sometime soon.
More questions?
So as far as I understand, we use this for theorem proving, and can we use this to check the type system of a given language or something like that? You're given a program in a given language, whether it's type safe or not.
Oh, okay. So one of the standard examples that people use for these kind of theorem provers is proving meta properties about programming languages. So the typical thing that you do for a programming language is you prove things like safety results. So you say, if I've got for any program that's been written in this language, if it's been type checked, then this particular memory safety property will hold of it. And so there's a little cottage industry of cranking out results like that. There's a gotcha, which is there's an undecidability result that you cannot check a language in itself. I mean, that's kind of point of Gödel's incompleteness theorem, is that once I'll back up. Once a language gets sufficiently powerful, and it doesn't have to be very powerful, it's just a little fragment of arithmetic you need. But if you can specify that little fragment of arithmetic in first order logic, then you cannot express your own correctness. So you end up with this funny kind of wobbly tower of correctness proofs, where you've got the language you're writing code in, then there's the language that you use to verify it. Oh, okay, but then what do you use to verify that? Well, then you'll have another language on top of that. And eventually that has to stop somewhere. And so the hope is that the place it stops is in a theorem prover that is so simple you couldn't possibly have got it wrong. Like, a few hundred lines of code kind of thing, where you can eyeball it and go, well, all right, I'll believe that. I mean, so Agda isn't there. I mean, Agda's source code isn't tens of thousands of lines of code. I mean, you can't eyeball it for correctness. But what you could hope is that you can have it verified in a language that's smaller, and now you keep on doing that until you eventually get to something that you just have to take on faith. I mean, eventually, these foundations of mathematics things, at some point you just have to go, well, all right, you know, I believe that. That seems like a sound foundation of mathematics. It will do me.
Thank you all. So next week.